Okay, so let's start with this example. So I'm taking an integral of y dv over a region E, and the region is what's hard. So the region is below z equals x plus 2. That's a plane. And above the xy plane, which is, of course, z equals 0. And between x squared plus y squared equals 1 and x squared plus y squared equals 4. This is a good time for you to pause the video and try to draw this region and figure out what the bounds are for your integral, and perhaps even compute the integral. Okay, let's move ahead. So what I should do, and I just have an A over here for no reason, so let's erase that. So what I should do is try to understand in polar coordinates what my region looks like. So I'm going to look at each of these remaining two objects. So x squared plus y squared equals 1, and x squared plus y squared equals 4. In the xy planes, these look like circles. That's y, and here's x. So this looks like a circle with radius 1 and a circle, pretty bad circle, let's try a little bit better, circle of radius 2. Okay? Because there's no z's in these equations, actually these are cylinders in R3. And so what I have in R3 is I've got this outermost cylinder, and then inside of it I've got this other cylinder. So let's draw this like this. And I'm looking at the region in between these two regions. And so in this plane, that's this region here. And so over here, it's filling in between these two cylinders. So it's a little cylindrical shell starting at radius 1 and going out to radius 4. And actually, the way I just described it kind of makes it easier to graph this. So another way to interpret these two functions is this innermost one. That's r equals 1. That's how we said cylinders look in cylindrical coordinates. And these are cylinders, so cylindrical coordinates should be useful to us. And this outer one here is r equals 2. Okay. And that's already it. So you are trying to describe, when we set up this integral, our bounds, to tell us how to do a for loop that goes over all of the points in this region. So what's my new volume form? It should be r dz dr d theta. Important to remember. I told you to memorize it. So my thetas, well, to hit every point in these cylindrical regions, I kind of have to go through every theta between, let's say, theta equals 0 and theta equals 2 pi. And so I'm imagining my region starting at theta equals 0 and going all the way around until it approaches and ends up here at theta equals 2 pi. And now imagine that you're at a given theta, some mysterious theta in between, and you ask yourself, okay, what do my r values go between? And r is going kind of radially out as theta is going around. And it's starting at r equals 1 and going out to r equals 2. And so now that's telling me to go over all of the points in this polar region in the xy plane, which you should think of as the base of our region. Now the actual region we want starts at the xy plane, and so let's draw this base down here. This is the xy plane. And we said that's just z equals 0. And it's going to go up to z equals x plus 2. I haven't really drawn any axes, but I know x plus 2, that's a line of slope 1, starting up at z equals 2. So when x is 0. So in some sense, that's like drawing a line like this, and then turning it into a plane. As usual, I don't think it's super duper important to exactly have the correct picture. Like, I don't know, for instance, in this picture, I didn't bother to check, does this plane go over and intersect, is it intersecting this point up here on the cylinder, or is it hitting somewhere lower? And like, I didn't quite figure out exactly where to put my intersection point over here. And so maybe I might need to take this plane and move it down, right? Well, let's figure it out. So what would be one of those points? That's like taking one of these points where x is as small as possible. So my test point here will be where x is smallest as possible. X could at smallest be minus 2 at that point, because we're at radius 2. And so if x is minus 2, z equals x plus 2 becomes z equals 0. So in fact, this does come down here and intersect. So I should be moving this intersection point down here. So the actual plane is going through something like this and cutting off my region. Okay. Which is good. Okay, and now I just do my z-bounds. So you imagine, again, you're at one of these points out here in this polar region. So that's this big green point here, or maybe it's this point over here, right? And you ask yourself, where does my z-coordinate start? I'm starting down here at z equals 0, and I'm going up in the z direction to this plane. And that's z equals x plus 2. So my final coordinates are going to be z equals 0 to z equals x plus 2. Okay, let me give myself a little bit of room to actually compute this integral. The innermost, I see I didn't do one thing, which is I have this y in here. So what is y going to be? Y is going to be r sine theta. So the actual integral I care about is the integral from theta equals 0 to 2 pi, r equals 1 to 2, z equals 0 to x plus 2. Oh, and then I realize, that x is also an issue, so let's maybe highlight our issues over here. That x should definitely become a r cosine theta plus 2. Okay, that's fine. And my inner integrand is now r squared sine theta d z dr d theta. And so one of those r's, just to trace it out, came from the y component, and one of them came from this extra r in the volume form. When I'm integrating, dz is as easy as it could possibly be. There's no z's around, so I just integrate and I get a z. So I get 0 to 2 pi, 1 to 2, r squared sine theta, z, and z is being evaluated from 0 to r cosine theta plus 2, dr d theta. Okay, z equals 0, we're going to get nothing, and when we plug in the r, we're going to get something interesting. So theta goes from 0 to 2 pi, r goes from 1 to 2, and now what I'm left with here looks like r cubed sine theta cosine theta plus r squared times 2. So when I evaluate at this for z. R squared 2 sine theta. And I've got dr, d theta. So The remainder of this is pretty straightforward. So, because we're now in polar, let's move up, and I'll give myself a little bit more room. When I integrate the r's first, everything else is now a constant, so I can do these in whichever order I want, both at once. The r's first, I get r to the 4th over 4 from this first one. R is being evaluated from 1 to 2. And then I've got the sine theta, cos theta. And let's leave the theta integral here. Plus r cubed times 2 thirds. R is being evaluated from 1 to 2. Sine theta. And all of that is still d theta. Okay? So plugging in r equals 2 and r equals 1, you should get something like, let's see, r equals 2, 4, 8, 16. 16 divided by 4, 4, minus a fourth times sine theta cos theta, plus 2 thirds r cubed, so r 2 squared, 2 cubed is 8, 8 times 2 is 16 thirds, minus 2 thirds sine theta d theta, and theta is going from 0 to 2 pi. And let's see, so this theta integral, for people who are still with me, I can do the first one as a u sub, so I can let u, sorry, I'm in my highlighting mode, so I can let u equals sine theta, so du is cos theta d theta, and I'm just integrating u here, and sine at both of those, at both 0 and 2 pi, is 0. So this is just going to give me 0, but I'll write that out. And this one, I just am going to integrate to get minus cosine, as I do the integral. So I think my final answer looks something like 4 minus a fourth. And then this part of the integral is going to give me u evaluated from u equals 0 to u equals 0. U squared over 2. Whew. And this other part, which that's giving me 0. This other part is 16 thirds minus 2 thirds times minus cosine theta, evaluated from 0 to 2 pi. And cosine theta at both of those points is the same, so the same thing's happening as over here. We get that this is also going to 0. So my total answer is 0. Big conclusion.